All right, welcome back. So we're still talking about transformations of variables, right? We know that the relationship between x and y maybe does not follow exactly a straight line. And so we might want to transform our data to get something that does have a straight line relationship, because ordinarily squares likes to fit a straight line. But keep in mind, it's okay to fit a straight line between some non-straight things, which will allow us to model non-straight relationships. So what I mentioned, the common transformation of doing a polynomial, which allows it to add some curviness. Another very, very common transformation is the logarithm. Logarithms especially get a lot of usage in the social sciences because we deal with a lot of highly skewed variables. So what a skewed variable is a variable where you have a bunch of observations that are relatively similar, and then you have a few observations that are way different. So take wealth, for example, right? The typical person's wealth is like a few $1,000s, maybe tens of thousands of dollars, maybe $100,000, right? If you look, depending on which kind of group you're looking at. But then compare that to somebody who's like really rich and has like billions and billions and billions of dollars. So you got most people way down here with you know, something in the thousands range, the tens of thousands range, and then you got the people who are sort of outliers and they are way bigger, right? And it's not just that we have outliers, it's the fact that the outliers are just so many times bigger than the mass. So this is a skewed variable. Most of the time in the social sciences, that is the direction of the skew, right? There are not a lot of variables in the social sciences where a lot of people are very big, and then you have a few very tiny ones. It's almost always in the other direction. A few sort of down here, and then big ones over here. When you have this, it can make your ordinary least squares model kind of mess up. Because remember, it is dealing with trying to minimize the sum of squared residuals. And so what are you going to do if you're a regression model and you're trying to describe something about these people down here, then you're like, wait a minute, I just described these people pretty well. Uh-oh, that person's way over there. And my residual for them is enormous because I'm like predicting their wealth okay, but this person I'm off by billions and billions and billions of dollars. And so I better change my model so that I fit that person really well, right? That's the concern really when you hear about outliers. Outliers are not necessarily wrong data, and in fact, outliers should affect your analysis. They're part of your data, but you don't want them to have undue and over influence on your model. That's the problem with outliers, really. So that's one problem that we might have in our data, that we have this big old skew. Another problem is that some relationships we don't think should be straight line relationships. They might be percentage or proportional relationships. So for example, let's talk about wealth again. Let's talk about, say, my wealth over time. Well, my wealth over time is going to be partially based on, I mean, how much I have in my savings account, and then also the interest rate on those savings, or perhaps, you know, my investments or whatever, right? You know, let's say that I'm going to regress my wealth on the investment return from my investments, right? Well, that shouldn't be a straight line relationship. If the return rate goes up by a certain percentage, that doesn't make my wealth go up by a certain number of dollars. It makes my wealth go up by a certain percent, right? And so there shouldn't be a straight line relationship between wealth and the interest rate. There should be a proportional relationship. If the interest rate goes up by 0.01, then that should multiply my wealth by 1.01. It shouldn't increase it by a certain amount. It should multiply it. So in either of those cases, these are problems that logarithms can solve. They solve the skew problem because what they do is they take those big old values and they keep them in the data, but they sort of scrunch them down so that there's not as much distance between them and the mass of the data, which allows them to still be in the data. They're still counted as data, but we don't get as much of a pull from them on our model. They also solve the problem of percentage interpretation because logarithms have a very convenient proportional interpretation. In particular, we know that if you take the logarithm of x and the logarithm of y, then that's the same thing as the logarithm of x times y, which can be pretty convenient, right? Because if we're talking about a 1 unit increase, say, as we would get from our regression model, a 1 unit increase in x is associated with a coefficient size unit increase in y, right? Those are both additive increases. Well, let's just move that increase around. So let's say instead of adding 1, we're adding, let's say the log of e to the 1. That's the same thing as adding 1, right? And then the log of the e to 1 and the log of x, if we're adding this to this, pop them together. And now suddenly we are multiplying our original x by e. So if you didn't follow that math, it's okay. My main point is that we can take a linear increase and turn it into a proportional increase using a logarithm, which is something that will allow us to model proportional relationships. So that's why we would use a log. We might log a variable if it's heavily skewed, and we might also log a variable if we want to model some sort of proportional relationship with it. And it's easy enough to do in a regression. We just take a regular regression model and plot a logarithm on one of the variables. So for example, in this model, we are regressing y on the logarithm of x. Great. So then the problem is, how do we interpret these coefficients once we have them? How do we get that proportional relationship that I just said that we were going to be able to get? So it turns out that the same thing that we talked about before still works. A 1 unit increase in the predictor is associated with a coefficient-sized change in the outcome. That still works. The only problem is that now the predictor that we're getting a 1 unit change in is no longer the variable that we're actually interested in. I don't care about a 1 unit change in the log of x. I want to know something about the proportional change in actual x. So how can I make that conversion? Well, there are two main ways to do it. One is the sort of correct way, and the other is the approximation way, and I'll talk about both of them. So the correct way is to actually do the conversion that I mentioned before, where if you have a certain sized increase in x, well, you convert that into something with a logarithm, you multiply, you bring it into the thing, and then you can see the proportional change that you have. So if we're regressing, say, the log of y on x, and we'd say the 1 unit change in x is associated with a coefficient-sized change in the log of y, well, if I want to convert that to a change in y itself, well, I'd say, okay, all right, we have a beta 1 unit change. That is the same as the logarithm of e to the power of beta 1, right? The logarithm of e to the power of anything is just the thing. If we're talking about a natural logarithm, which we in social sciences always are. So now we have the logarithm of y plus the logarithm of e to the power of beta 1. That turns into the logarithm of y times e to the power of beta 1. So now we know that we have increased y proportionally by e to the power beta. So if you're talking about some sort of increase, then what you're really talking about is a proportional increase of e to the power of whatever your coefficient was. Now say we're regressing y on the logarithm of x, and I want to know the effect of a proportional change in x. Well, we can do this whole process sort of backwards. I can say, well, what would the effect of a 1% increase in x be? Well, that would be looking at, okay, what's the logarithm of x times 1.01, right? Because that would give us a 1% proportional increase in x. So now we have logarithm of x times 1.01. We can pull that out. We get now the logarithm of x plus the logarithm of 1.01, right? And so we calculate the logarithm of 1.01. We say, okay, that is how many units the log of x has increased by. So what we get now is the coefficient beta 1 times the log of 1.01. That is how much our y is going to increase by. So that's the accurate way of doing this, to actually go through the process of thinking, okay, converting a linear change, which we are getting from our regression model, into a proportional change that we can actually interpret. And this can go from either turning a linear change into a proportional change, as I just walked through with the y, or turning a proportional change into a linear change, as we walked through with the x. And you're thinking, oh my goodness, that's so much work. Why can't I just, do something a little bit easier? And there is an approximation that will allow us to do this a bit more easily. And the approximation works like this. It just so happens that the logarithm of 1 plus something is very, very similar to just that something, as long as that something is very small, right? So, for example, the logarithm of 1.05 is roughly 0.05. The logarithm of 1.01 is roughly 0.01. The logarithm of 1.1 is roughly 0.1. So we can use this to sort of approximate whatever our proportional increase is, just the linear increase. Now, this isn't exact. This is an approximation. And in fact, it is an approximation that breaks down rather quickly as the thing gets large. So you would not, for example, say that a 50% increase in x, which would be a 1.5 proportional increase, is about the same as a 0.5 increase in the log of x. That doesn't work anymore, right? So for this to work, we really need that increase to be in the order of like 0.1 or lower, 10% or lower. If it's bigger than that, you might want to steer clear of this particular approximation and do things the proper way. But let's walk through this approximation and see how it works. So let's walk it through with the three different sort of versions that we might have of our regression model with logarithms in it. So first, let's talk about the regressing y on the log of x. We will start with our sentence and we will convert it one stage at a time into something we can use. A 1 unit change in the log of x is associated with a beta 1 sized unit change in y. Great, that's our original sentence, good to go. Now, what we're going to do is we're going to scale this whole change down so that it's small enough that our approximation will work. So let's just divide everything by 100. So let's say a 0.01 unit change in the log of x is associated with a 0.01 times beta 1 unit change in y. Great, now we are small enough. Now that 0.01 unit change in the log of x is small enough that we can do our approximation. And by our approximation, a 0.01 unit change in the log of x is approximately a 1% change in x. So now we can say a 1% increase in x is associated with a 0.01 times beta 1 unit increase in y. Great. So that's y regressed on the log of x. What if it is the log of y regressed on x? A 1 unit change in x is associated with a beta 1 unit change in the log of y. So again, we might need to scale this down. We might not need to, depends on what beta 1 is. If beta 1 is already like 0.01, we're probably good to go. If beta 1 is like 3, then we got to do some work. So let's assume that beta 1 is big enough that we got to scale it down. Let's also divide it by 100. So now, a 0.01 unit change in x is associated with a 0.01 times beta 1 unit change in y, or in the log of y, sorry. Okay, great. So now let's convert that 0.01 times beta 1 unit change in the log of y into a change in y. So we can just turn it into a percentage, basically. So if it's a 0.01 times beta 1 unit change, that turns into a just beta 1% change in y. Lastly, let's talk about the log of y regressed on the log of x. Now, conveniently in this case, the sort of approximations just sort of cancel each other out here. And so whatever conversion we do is just going to get converted back, so we can work on it a little bit more simply. So I can say something like a 1 unit change in the log of x is associated with a beta 1 unit change in the log of y. If we work through all the steps, it'll all sort of come back to where we started. We'll end up with a 1% change in x is associated with a beta 1% change in y. So that's how we can interpret a model with logarithms in it, and also what logarithms do for us. Now, there are some issues with logarithms in particular that we'd like to use them where they don't really belong. Logarithms have a problem, which is that they cannot accept negative values or 0. Now, negative values is not really a problem. It's kind of rare that you have a variable that takes negative values that you want to take the logarithm of anyway. But zeros are a problem. There are a lot of variables that take a value of 0 sometimes that we might want to take a logarithm of. So like income, for example. Income is highly skewed, and yet there are a lot of people who earn 0 income that we might want to include in our model. We can't just take the log of it because we got all those 0 people in there, and the log of 0 is undefined. So what can we do in that case? Well, if the variable's on the left-hand side, we're talking about the log of y, then you could probably just, get rid of the whole logarithm thing entirely. You might want to use something like a Poisson regression or something like that. If it's a log of x, though, you can't just turn it into a Poisson regression, and you might have a problem. Well, in that case, you can sort of fudge things a little bit. What a lot of people will do is they'll just add 1 to the variable, take the log of 1 plus x, or they'll use something called the asymptotic hyperbolic sign transformation, which does something kind of similar. Now, both of those, they will allow you to estimate the model. They will allow you to include the zeros. They will solve the skew problem just like a regular logarithm would. They do mess up the percentage interpretation a bit. And in particular, at smaller values of x, the percentage interpretation doesn't really apply, which makes sense. Like if you're talking about including values of 0, what's a percentage increase from a base of 0? It doesn't really exist, right? So it makes sense that it's going to be sort of messed up there. You can do these sort of fudge transformations where you basically make a version of the log that allows for zeros. But then you got to be careful with the percentage interpretation thing that I mentioned. The calculations get a little bit weirder, and you probably want to make sure that all your variables take very large values because things are weirder down near the bottom. So you get this weird result where your percentage interpretation works better if you report income like in terms of cents than it does if you report it in terms of thousands of dollars, and that's kind of weird. Anyway, that's how we can include logarithms in a regression model and why we want to do it. Thank you.